using the time of operation. For example, this propellant total propellant is 2.5 minutes. By knowing the rate, so you multiply in seconds. So 2.5 minutes equivalents to 150 seconds. Okay, so then you multiply, you will get the weight as well as the the weight of the oxidizer, the weight of the fuel, and then the volume of oxidizer, volume of the fuel. And then maybe you want to ask, okay, since it is 2.5 minutes, but why it is 152? This is allowing the 2 additional seconds for start and stop transient condition. So transient condition, 1 second to start and then 1 second. That is why they use 2 seconds. So 150 plus 2 seconds is 152. Okay, so from the nozzle theory, and now we designed what will be the weight of the propellant, volume of the propellant, which is the size of the propellant. And then these are some of the properties of propellants, liquid propellants that we have. Like I said before, there are several characteristics, desired characteristic what we want from the liquid propellants. Of course, we want the fuel to have high heating value, so that during the combustion it can generate a lot of heat energy, which can later be used to convert this into kinetic energy as well as thrust. And also, like I said, we also desire to have fuel which have low specific gravity. So why we need to have low specific gravity? So that we can design the tank small or compact as possible. So this is to reduce the weight or reduce the size of the tank. Okay. Of course, other than that, what we want from the fuel is to have the product after the combustions to have low molecular mass. This is the desired one. Okay, and during the burning in rocket, yes, we burn the R, which is oxidizer to fuel ratio around 3 to 6, but in terms of stoichiometric condition, we burn at the rate condition. Why? Because we want to produce a lot. We want to have a large amount of low molecular mass reaction products. Okay, that is what we have learned so far last week. So let us continue in this chapter 1.5, common physical hazards. Of course, this is some of the main one. We do have many things. The first one is corrosion. When you deal with this type of material, such as nitrogen tetroxide, nitric acid, nitric oxide, or hydrogen peroxide, it tends to corrode your pipe. It tends to corrode the thrust chambers and also the tank. So these are some things that you need to avoid danger, because it is you can what do you call it, reduce the structural integrity of this tank, for example. Okay, and it can cause leak. Fire hazard, of course, you cannot avoid this. All you are with very energetic propellants, so it is flammable and it can ignite easily. So for example, nitric acid, nitrogen tetroxide, fluorine. Fluorine is a good propellant because it gives you a huge amount of energy. But anyhow, fluorine, liquid fluorine is very, what do you call it, dangerous for human health. All right. Hydrogen peroxide reacts spontaneously when it causes many organic substances resulting in fires. So that is why you need, it is not just during the operation, maybe during the transportation, maybe during the refilling and storage as well. Health hazard, of course, when you deal with hydrazine, monomethyl hydrazine, and then your unsymmetrical UDM hydrazine, those are materials, those are propellants which is very hazardous for human. Okay, it can cause what do you call it, health problem. Explosion hazard, okay, you have fire hazard, now explosion hazard. When you deal with hydrogen, when you deal with liquid oxygen, those can be very explosive. And in this condition where you have, because hydrogen and LOX, liquid oxygen, those are what do you call it, stored in liquid at very low temperature and at very high pressure. So when you have done this experiment in your high school, when you have a hydrogen gas, any any fire nearby, it can cause explosion. Explosion and fire are two different things. Okay, explosion when you have a pressurized container, pressurized container, and then the pressure suddenly changes. So when for example, abrupt, okay, so pressure from high pressure to low pressure, this is where explosion comes in. Okay, the explosion happen. Okay, accident spills, it is of course during the engine operation. If you look at the statistics of major accidents during the launching or during the operations, many accidents happens in terms of percentage, 60 to 70% are due to the propulsion system lah. So including the thrust chamber, maybe leaking at the feed system and etc. So it is this area is quite hazardous and quite dangerous. And last one, of course, material compatibility. So when you deal with something with metals and non-metals which you want to combine or which you want to stick to, okay, so this usually cause material compatibility accidents. Okay, maybe it doesn't fit, or maybe there are some loose, all right, and then maybe there are some leakage and etc. So usually they are using a gasket or O ring. So these are some of the common physical hazard happen in rockets. Okay, like I mentioned just in last week, these are some of the desirable physical properties other than the heating value, other than the what do you call it, low molecular mass. Uh, we need to have a propellant which has low freezing point. So it permits the operations of rockets in the cold environments. So you know that at high altitude it is cold, right? So when you have low freezing points, so this okay, to avoid that the propellant solidified. And then of course you want stable propellant so that the propellant does not decompose from liquid during the operation or storage even at elevated temperature. So you want to have a propellant that is maintained, not decomposed. The third one, in terms of pumping properties, you want to have a propellant which has low vapor pressure. This is to permit and also not only easier handling of propellant but also more effective pump design in application where propellant must be pumped. Okay, you want to have a low vapor pressure propellant. Next is high specific gravity. Like I said just now, the denser propellant provide a larger propellant mass for given vehicle tank volume. So this permit a smaller tank volume, which then later you will have lower structural vehicle mass and lower aerodynamic drag. Why do you have low aerodynamic drag? Okay, so when you can build a tank which is compact, which is small, so your rocket body is not fat, it's not big, so you can have like a slender body of rockets. So this will reduce the aerodynamic drag, including frictional drag lah. Okay, the propellant density increase will allow increase in mass flow and total propellant mass. The fourth one is heat transfer property. You, like I say, you want to have a propellant which has high specific heat, high thermal conductivity, low freezing temperature, and high boiling or decomposition temperature are all desirable properties for the propellant used for thrust chamber cooling. And the sixth one is temperature variation and physical property. So during the temperature variation in physical properties of any liquid propellant, they want to have this temperature variation should be small and should be very similar for the fuel and oxidizer. So they don't want to have a effect when you deal with temperature which is from cold to very extreme temperature. So you hope that these properties of the propellant doesn't vary that much in terms of temperature variation. Okay, all right. So let's look at the ignition, combustion, and flame properties. I do have figure here. All right. So before that, let me tell you what is ignition is all about. So when you have hypergolic propellants, hypergolic propellants like a propellant that can ignite, self-ignite automatically. So these are very spontaneous propellants, and all rocket propellants should be readily ignitable. This and exhibit acceptably short ignition time delay. You want to have ignition time delay very short in order to eliminate potential explosion hazard. So what you want is the fuel can be easily ignite. Okay, either you want to use hypergolic propellants or non-spontaneous. Why? Because you want to reduce the ignition time delay. Non-spontaneous ignitable propellants, which is not a hypergolic propellant, okay, this must be energized by external means, for example, for the ignition to begin. So you know that when you have both oxidizer and fuel in one place, you need to have heat source, so for ignition, so that it can combustion happen. Igniters are devices that accomplish localized initial chamber pressurization and initial heating of the propellant mixture to a state where steady flow combustion can be self-sustained. So when you ignite, the fuel and the oxidizer combust, and then you have a flame. All right. Certain propellant combination burns very smoothly without vibration. Vibration, in other words, we say that it is a gas pressure oscillation. So why you have gas pressure oscillation? Because inside the combustion chamber, you have turbulent flow. So this turbulent flow will have vortices. You're going to have different spots of pressure location. So this local pressure, this variation of pressure will tend to oscillate the gas inside, and when this oscillation cannot be controlled, you can have a structural failure. Other propellant combinations do not exhibit such combustion stability and therefore become less desirable. So this is example of the injector. Okay, the left hand side. You can sometimes it looks like this. Sometimes you have different look. But anyhow, the holes are very small so that the fuel can atomize. So what will happen in the thrust chamber? First of all, you have an injector. Okay, so this injector will be at the left end. So this injector will spray the liquid jet or liquid propellant enter the chamber at a relatively slow velocity. How slow is slow? You are talking about 20 meters per second to 100 meters per second during the injection. Sometimes, of course, you are injecting gases, propellant like hydrogen, because well, although you are bringing liquid hydrogen or liquid oxygen, when it is enter the injector, okay, it is already vaporized, it is already becoming a gas. And then probably in the injector you are having a partial evaporation of liquid, and this interaction of jet or spray with high pressure hot gas. Okay, so you have a gas, and then what will happen later after the injection? You do have atomization. Okay, atomization is some impingement and breakup of jets of sheet. Sometimes during the atomization, it is in the form of droplets. Sometimes it is in the form of sheet. Okay, spray in terms of sheet. And this formation of liquid, sometimes it is look like a liquid fan or spray cone. You do have formation of droplets, and you do have secondary breakup of droplets. So you have droplets and then another breakup, and this is a liquid mixing, and some liquid chemical reaction happen during this atomization. You do have oscillation of jets or maybe sheets fan, and then becoming unstable during the breakup. Evaporation begins and some vapor reaction occur. So you have injection and then atomization. So this breakup, all right, either droplets or sheet lah. And then when you have this breakup, droplets atomize, so you have vaporization. Okay, vaporization. So droplet gasification and diffusion. What do you mean by gas diffusion? Gas going inside the combustion thrust chambers. Okay, you have a further heat release from local chemical reaction because you do have chemical interaction between fuel and oxidizer. So you do have a heat release. When you do have a heat release, temperature rise up, relatively low gas velocity and some cross flow, of course. Heat absorbed in droplets by radiation. So in terms of heat transfer, what happened? You do have heat transfer due to radiation. You do have heat transfer due to convection and conduction. Some blowback of turbulent gases from hot reaction zone into injector zone, and then the acceleration to higher velocity and evaporation rate influenced by the turbulent pressure or temperature oscillation and acoustic wave. So during this evaporation, it involves all those heat transfer mechanism. And then when both liquid oxidizer and fuel atomize or not atomize, evaporate, and then you do have the mixing and reaction. So you do have, you know that it is swirling, you do have a turbulent flow, and you have turbulent mixing in a 3 dimension. It's mixing and reaction region. Multiple chemical reaction and major heat release happen. Of course, when what you have learned in chemistry, it is just a one-step reaction, reactant to product. But when you do have high temperature, high pressure, you have multi-step reaction. So this interaction of turbulence with droplets and chemical reaction happen, temperature rise, reduce the density, and increase the volume flow rate. Okay, you do have a local mixture ratio rates or velocities are not uniform across the chamber because of this very rapid change in time. Okay, you do have, since it is a 3D flow, so some of the tangential and radial flow much near the injector region. So you know that during rapid combustion zone, this mixing reaction happen inside this combustion zone. You do have turbulent, in a very high intensity of turbulent flow, side and then vortices and etc. And then you do have this stream tube combustion zone. What's happening here? The chemical kinetic cause the attainment of final combustion temperature final equilibrium reaction for the gas composition. And then since you know that here the velocity is still subsonic, so since the area reduces according to the incompressible flow, it start to accelerate. Okay, so the gas start to accelerate high chamber velocity, and then gas dynamic display turbulence, increasing the axial flow of the gas. And then of course you have boundary layer at the wall. It looks like it is streamlined. Okay, and the flow towards nozzle, heat transfer to the wall accelerated until it reaches the throat area, and then it's already at supersonic. So you are talking about compressible flow, and then you do have a diverging session. It start to accelerate and then becoming more high velocity, and then exit at the nozzle exit. Okay, so this is where the gas expanded supersonic expansion zone. So this is what happened inside the thrust chamber. Next, all right. So the liquid oxidizer and fuels, what we have, the most energetic known oxidizer producing high specific impulse and having the highest density is liquid fluorine. Okay, like what I said just now. You do have liquid oxygen, oxygen difluoride, chlorine difluoride, and chlorine pentafluoride. You do have LOX, liquid oxygen, hydrogen peroxide, O2, nitric acid, HNO3, nitrogen tetroxide, N2O4, and nitrogen oxides. Those are oxidizers. And then in terms of fuel, you have aniline, sulfuryl alcohol, gasoline hydrogen hydrate, borohydrates, methyl, ethyl alcohol, ammonia, and some of the mixture of this. In terms of hydrocarbon fuel, families such as jet fuel, kerosene, F gas is aviation gas, RP1 and RP2, and also methane. When you mention about hydrocarbon fuel, you do have what do you call it? Carbon, C and H in the molecular structure. Liquid hydrogen, hydrazine, and then of course you have MMH, UDMH, and other similar physical and thermochemical properties of fuel. Those are all gas and liquid. Those are liquid. You do have gas propellant. Okay, so it is stored as a gas at ambient pressure or cold gas. Of course, this is much simpler because you only deal with gas. Okay, the reaction control, which is RCS, it has been matured enough, more than 70 years, and the engines components are relatively simple as compared to a liquid propellant. So you don't have to use injectors, atomizers, and others. Multiple simple nozzles, often aluminum or plastic, each with the electric control valve or pressure transducer and provision for filling and venting. Selection of propellant gas, storage tanks, and RSA design depends on, of course, many factors such as volume, mass, storage tanks, the maximum thrust and total impulse gas density, required maneuvers, duty cycle, and flight duration. So gases propellants are much simpler, low cost, and as compared to liquid propellants. So these are some of the core gas used for rockets: hydrogen, helium, methane, nitrogen, air, argon, and krypton. Okay, you can see those are the so it means that this propellant, does combustion happen? Yes, it can be, combustion can happen, and also without combustion, like a coal gas. So if you have combustion, means that you are talking about high thrust, high pressure, and high temperature lah. Okay, so maybe during the primary propulsion, maybe during the ascending, maybe during the boost, application. But if you are using this gas for auxiliary, so you don't have any combustion happen. So in terms of the propellant tank, you have different types of orientations or arrangement of the propellant tank. Okay, you carry this in the rocket body. So in a liquid bipropellants engine system, the propellant are stored separately. So you have oxidizer in one tank and then fuel in another tank within a flying vehicle. Tank can be arranged in variety of ways and design, shape, and the location to apply some control over the change in the location of vehicle center of gravity. So, brothers and sisters, you are if you bring liquid propellants, you can see that the liquid in the tank moves. Okay, so because the rocket move. Okay, so when the liquid move, rocket move, so this will tend to adjust or adjust the vehicle center of gravity. So that is why you need some what do you call it mitigation, so that this fuel or this propellant doesn't change too much the center of the gravity. If center of gravity changes drastically. So this is where the rocket can crash or diverted from the desired trajectory. So there are several mitigation to avoid this. You can imagine like a fuel tank in a fuel tank, the lorry, okay, the lorry who carries fuel. You can imagine that the fuel inside changes when the lorry moves, kan, when the lorry turn uh, and then accelerate and then decelerate. So all those designed mitigation to avoid the change of center of gravity too much. uh, there are several methods lah. There are several methods to avoid this. Because propellant tanks also have to fly, their mass cannot be neglected. So you also must consider the what do you call it, usage, the usage of liquid. So the tank of fuel and oxidizer, the mass reduces. Why? Because it is during the combustion. So this also might tend to adjust the center of gravity, not just the residue of the fuel, but the fuel that is being used for combustion. Common tank materials are aluminum. Sometimes materials used are aluminum, stainless steel, titanium, and also alloy steels. And to what do you call it, to save the weight, fiber reinforced plastics are being used. So, all right. So the arrangement can be, for example, if you are using a spherical tanks, a tandem tanks with external piping, the second one. The third one is a tandem tank with a common bulkhead, but using the internal piping. You do have concentrate tanks and multi-tank. Okay, so these are some of the arrangements. So what happened, okay, inside these tanks? So it is necessary to have a space. You have a allowable space. This is something we call as ullage, okay, ullage, okay, that allows, you must have, when you want to design a tank, you must also to consider thermal expansion for this propellant, and also for the accumulation of gas that will originally dissolve in the propellant, or with some propellant for gaseous product from any slow chemical reaction within the propellant during storage. So you cannot fill the tank 100%. You must allow a necessary space for this. Depending on the storage temperature range and the propellant coefficient of thermal expansion, Okay, and on the particular application, ullage volume, which is the necessary space that you must allow, range around 3 to 10% of the volume. Okay, like I say, you cannot fill up the propellant 100%. You must give some allowance space, ullage, around 3 to 10%. The expulsion efficiency, which is when you want to expel out the propellant out from the tank, of a tank or propellant piping, is the amount of propellant that can be expelled or available for propulsion divided by the total amount of propellant initially present, around 97 to 99%. Of course, in terms of the geometry, the optimum shape for propellant tanks or for gas pressure tank is spherical. Okay, the optimum shape, it is spherical. This is to my surprise. Why this is the optimum shape? Because for a given volume, it results in a tank with a least mass. Okay, from this tank spherical shape, it can reduce your mass. But unfortunately, there's a, what do you call it? Nothing is a free lunch. Larger spheres, which is the large spheres tank, we need fat body. Okay, so if you want to have spherical tank, you need to increase the diameter of the body, which in turns make your rocket bigger in size, fat in size, and increase in aerodynamic drag. Okay, so this is the downcash. That is why, although you can save the inert mass, but it will result in increased aerodynamic drag. Cryogenic propellants, for example, you are using liquid hydrogen or liquid oxygen, cool the tank wall temperature far below the ambient temperature. Okay, you are using cryogenic fuel, which then later cause condensation of moisture. So cryogenic fuel, for example, liquid oxygen or liquid hydrogen, okay, you can see that it is negative 100 something degrees Celsius. So what happened is that at the wall of this tank, condensation happened. So condensation happened at the tank wall. So because of this low temperature, you can see that there are formation of ice started to appear during or prior to the launch. This ice formation at the wall of this tank, it is undesirable. Why? Because it will increase the inert mass of the rocket. With the ice formation at the wall as well, it can increase the friction drag. Okay, so this is the thing that you must consider if you are using cryogenic fuel. Condensation happened, ice formation started to form at the wall, and you can, because of this, the inert mass will be increased. So several categories of tanks in a liquid propulsion system. Okay, SFIT system. The propellant tanks typically operate average between 1.3 to 9 megapascal, which thick walls and heavy. For high pressure stored gas, you are talking about the pressure between 7 megapascal to 70 megapascal. These tanks are usually spherical for minimum inert mass. If you have a turbo pump feed system, okay, it is necessary to pressure the propellant tank slightly above the pump cavitation, the average value between 0.7 until 0.34 megapascal. Okay, so how to avoid or how to mitigate this oscillation happen inside the tank? Okay, so the liquid, the rocket is moving, so the liquid inside the tank also move, so oscillation happen, side acceleration also uh, Set acceleration of vehicle in flight also may cause. Number one, okay, when you have this sloshing, when you have this oscillation, you do have sloshing, you do have vortexing. Sloshing happens, so this allow gas bubble in the feed line and can cause irregular shift in vehicle center of gravity, making flight control difficult. And next one, due to oscillation or side acceleration, vortices happen, vortexing happen. So vortexing happens when you allow the gas to enter the tank outlet pipe, and this phenomenon is similar to Coriolis effects. When you have a bathtub, you want to drain the water from this bathtub. So these vortices can be augmented by the vehicle spin or as well from the rotation in flights. So you are expecting sloshing, you are also expecting vortexing inside the tank. So how to mitigate this? There are many methods. Okay, these are the two methods being used. One is using positive expulsion device, such as you have a movable piston inside the tank so that it can keep the fuel from sloshing, from vorticing a lot. So you have a movable piston. Or maybe you have inflatable bladders inside the tank or thin diaphragm. Okay, diaphragm like our lung. Okay, so that it can close the gap so that this liquid propellant doesn't move that much. You do have a surface tension device which only, but this surface tension, it's relying on the surface tension force to keep the outlet covered with liquid. Okay, so these are two types of mitigations technology inside the tank to avoid the sloshing or vortexing inside the tank. 3.0 propellant feed system. Okay, you know that you require a pipe, you require many pipes from the tank to the thrust chamber. The primary functions are two. Number one, of course, you need to raise the pressure of the propellants. Okay, when the fuel enter a pipe or oxidizer enter the pipe, the pressure will drop. So in order to maintain the pressure inside the pipe, you need to raise it up. So that is why you need to have a pump inside the feeding system. You also need to supply them at the design mass flow rate to one or more thrust chamber. So the function of feed system to raise temperature and to supply the mass flow rate desired. The energy for this function can become either from high pressure gas, centrifugal pump, which is a turboprop pump, or the combination of two. Okay, this is the diagram, the our first class diagram. It is either through high gas, okay, or it is through the turbo pump. Okay, all right. So the selection of the feed system depends, of course, the rocket application, which is the mission, the duration, number of thrust chamber, the experience, the mission, and also general requirement for the simplicity of the design. I think this is too blurry for you. Okay, let me read. Okay, you have a liquid propellant feed system divided into two. You have in the left is pressurized system. The right one is turbo pump system. Okay, turbo pump system. So inside the pressurized system, you have direct gas pressurized system, flexible bag within the tank, and piston pressurization. You have pump, you have turbine, and also you have gas power supply and gas discharge. I took this snapshot of figure 6.5 in Sutton book. I hope you do have this. And from the pump, you have many. You have either multi-stage impeller or single-stage impeller. You know, pump, impeller is something. The function of impeller similar to compressor, but the geometry of impeller is different to compressor. Okay, compressor, the shape can be in the airfoil shape, but impeller, it is kind of blades like shape. Okay, so the function is the same to raise the pressure lah. Okay, so classification only two feed system, one for the pressurized and one for the turbo pump system. So all the feed system consists of pipe, like I said, pipe, a series of valves. So you have drain valve, you have gas bleed valve, and then you have gas fill valve, you have check valve, and then you have tank vent valve. So this valve to check whether to control the supply of this gas or propellant. Okay, inside the valve as well, you do have pressure regulator. Controller lah, controller. Provision for filling and usually also for removing the drain flushing. The liquid propellants, filters, and control device to initiate, stop, and regulate their flow operation. You have local pressure and flow. Okay, why do you need to have a local pressure? Local pressure is you want to measure a pressure at certain location. The highest pressure resides in the high pressure gas supply tank. Okay, so you have high pressure supply tank. Okay, the pressure then drop along the pressurizing gas subsystem. Of course, inside the valve, inside the pipe, the pressure drop, like what I said. Okay, and then it will drop further in the liquid propellant flow subsystem inside the pipe, valve, filters, injector, or cooling, as the liquid propellant flow into the thrust chamber where they burn at the chamber pressure. Okay, so you know that is why you need to make sure you have a pressure regulator, many pressure regulator inside the pipe, so that you want to see whether the pressure is enough before the combustion happen. Okay, all right. So this is for high pressure gas supply, and this one, if you want to pressurize using a turbo pump system, this is a turbo pump system before it enters the thrust chamber. So why do we need to know the local pressure? Number one is to find to know the stress. Okay, along the feeding system. Sometimes stress analysis, okay, and sometimes you want to know we want to conduct a thermal analysis of the related component subsystem. This is number one. Number two, for rocket calibration, so that the engine will operate at the intended mixture ratio, because when we designed the fuel to have R equal to 6, so we want to make sure that the pressure inside the feed line meet the target, right? Chamber pressure or thrust such tasks are accomplished by using a control device or simple orifice to adjust the pressure. The last but not least, we want to know the health monitoring system, to identify any discrepancy between what you have designed and then what is happening. Okay, it's a real-time basis. So that is why we need to know the local pressure. That is why you can see in the full rocket engine diagram, you have many pressure transducer inside the feeding system. All right, so 4.0 gas pressure feed system. Okay, like I said, it is one gas pressure feed system. Okay, so you are talking about this one. Okay, this gas pressure feed system. Okay, so it is the simplest one because you don't use turbo pump. Okay, the most common means of pressuring the liquid propellant and force them out their respective tank is the use of high pressure gas. So like in this tree diagram, so you are talking about pressure system. Okay, this is the pressure system. This is a turbo pump system. So we are talking about pressure system. So pressure system using gas pressure. Okay, so you have two types of pressurized feed system. You have a gas pressure regulator, which is the gas feed line with the engine operating at essentially constant tank pressure and nearly constant thrust, or you have a blow down feed system. Propellant tanks are large because they are store not only the propellant but also the pressurizing gas at the initial maximum propellant tank pressure. So what are the difference between those two? Reciprocating gas tank, but blow down types of gas pressurization require larger, heavier propellant tank. Advantage, of course, nearly constant pressure, but blow down is simple design, less gas required. Disadvantage of regulated pressure, slightly more complex. Regulator introduce small pressure drop. Gas stored under high pressure requires more pressurizing gas. But blow down disadvantage, thrust decrease with burn duration. Somehow higher residual propellant due to less accurate. Okay, so if you are using a blow down pressurized gas pressurized system, you actually have many residue. Okay, you have many residue. All right. So these are some of the, you can read this features of liquid propellant feed system in terms of enhanced safety, provide control, enhance reliability, provide usability, and also enable effective propellants. Uh, you can read this on your own. If you don't understand, please let me know. Okay, all right. Okay, so let's look at the source of pressuring gas. So you're talking about this one, okay? Source, pressuring gas. All right. So, in order to design or analyze any pressuring system, it is necessary to have relevant information about the tank and also the engine. Okay, so you need to know the propellant flow, how much that you want, thrust, how much you want to achieve, the duration, which is the period you want to burn this fuel, the pulse width, the tank volume, the percentage of ullage, and also the temperature, amount of unavailable residual propellant. So pressure in gas, usually for high pressure in a gas, they are using helium, nitrogen, or air. If you have gas created by chemical reactions, you the gas itself produce fuel rich gas for pressuring the fuel tank, and the other feed oxidizer rich pressuring gas into the oxidizing tank. You also need to have heated high pressure in a gas, so it is around 93 to 420 degrees Celsius. This is to reduce the amount of required gas. That's the inert mass of pressuring system, and this source of pressuring gas must have a direct injection. So for small stream hypergolic fluid into the main oxidizer tank, and small flow of hypergolic oxidizer into the fuel tank. So why you are using this type of gas? Because it is inert. What do you mean by inert? It doesn't create any chemical reaction with the propellants. So, what factors influencing the required mass of present gas? Of course, evaporation of the propellant. This happens. Okay, let's look at this tank. Okay, so this tank, for example, you're giving what do you call it, helium gas inside this tank. Okay, focus at that tank. So factors influencing required. Okay, what are the factors? Number one, evaporation of the propellant. This happened at the interface between the pressure and gas, and the liquid propellant is a key phenomenon. So when you introduce gas, inert gas, okay, to pressurize the tank, to pressurize the liquid propellant, there is a interface happen between pressure and gas, yeah, which is helium, and the liquid propellant. Okay, the evaporated propellant. Okay, you know that when you introduce gas inside the tank, propellant tank or fuel tank, you have the propellant start to evaporate. Okay, evaporate because pressure changes. Okay, so the fuel start to evaporate and it dilutes the gas and changes its expansion properties. So actually, this happen. Okay, this change depends on the temperature difference between the gas and the liquid sloshing, vapor pressure of the propellant turbulence, and local gas impingement velocity. Okay, so factors influence the evaporation of the propellant. Number two, aerodynamic heating. Okay, so when you introduce other chemical inside this fuel tank, okay, the temperature of those propellant walls which form part of the exterior surface, the vehicle surface exposed to the atmosphere. So you have such an heating can increase the gas temperature as well as the liquid propellant temperature, augmenting liquid evaporation. So when it exposed to the atmosphere, when it exposed to inert gas of this pressurized gas, so it start to heat. Okay, temperature start to increase. Condensation, water vapor in warm gas happens, so the condensation can also occur on the exposed wetted inner walls of the propellant tank, and this require more pressuring gas. Changes, of course, when you it is exposed, condensed, temperature changes. A cold gas will absorb heat and from the propellant and the engine hardware. This particular nature of expansion will depend largely on the time of rocket operation. And lastly, of course, you have chemical reaction. Some that can generate heat or increase the pressure. For example, you are thinking about exothermic reaction and etc. Okay, so it depends on the temperature difference. It can cause additional heating or cooling on top of the top liquid layer. So when you are trying to introduce inert gas to pressurize the liquid propellant, to pressurize the fuel, for example, these are some of the factors influence or what will happen with the pressuring gas or as well as the liquid fuel. Evaporation, aerodynamic heating, condensation, change in temperature, as well as chemical reaction. So that is why choosing the right pressuring gas is important. Okay. Six. Okay. We are almost there. We almost finished this chapter. Rocket engines for maneuvering, orbit adjustment, and attitude control. Okay. How do you look at this diagram? You look at this circular diagram. Okay. It is from the top of the rockets. So you have from the top of the rocket, it is circular, and then the bottom part is your thrust chamber, main thrust chamber. So the side wall where you have mini valve or mini nozzle at the side of the wall or side of the body of the rocket, this is for auxiliary. Okay, whether for maneuvering or for orbit adjustment or attitude control. So you can imagine, you have a tank and you have pressurized gas to pressurize the tank. So this tank also needs to pressurize the auxiliary thrusters. Okay, so engine usually include the set of small thrusters at the side wall that are installed at various places in the vehicle and common pressurized feed system. Okay, common one. So for example, this one to control the tank as well as the small thrusters. They are called reaction control system, auxiliary rocket propulsion system, or attitude control system. Usually, the small thruster, it is around 0.4 to 4 kilonewton of thrust. It's not that much. Okay, so the common method for achieving accurate velocity correction or process and angular control is to operate some of the in a pulsing mode. Okay, so you can imagine that to what do you call it, to control, to maneuver the rockets, the side forces, the side thrusters need to operate as well. Okay, maybe it is in pulses, maybe in longer period of time. Okay, you can see at the site of the rockets. Okay, the application, of course, some is I rarely see that it combustion happen there. It is only injected coal gas at the site. You don't have combustion there at the site. The application of pure torque to separate to the application of pure torque to spacecraft can be divided into two classes. Of course, the mass expulsion system, rockets, and non-mass type. The non-mass type, okay, this one is a mass type, means that you expel propellant to the side or to out from the nozzle. Some are using non-mass type. Non-mass type, you don't expel anything. This include momentum storage, which is the flywheel, gravity gradient, solar radiation, and also magnetic system. Okay, so you have to produce torque, you have mass expression type and non-mass expression type. This one is the last slide for this chapter. Safety and environmental concerns. Okay, brothers and sisters, it is necessary to be very conscious of all likely risk and hazard. You know that you are dealing with very flammable, very explosive materials, so it is very risky and hazardous. And then sometimes it can be very toxic. If you are, for example, if you're using hydrazine, of course, hydrazine or fluorine, those two types of propellants are very good, but it is very toxic. Okay, explosive fires or spill dangers. Before an operator or assembler, maintenance mechanic, supervisor, or any engineer is allowed to transfer or use any particular propellant, they must receive safety trainings in that particular propellants, because all those propellant needs very specific skills to operate. Its characteristic is safe handling or transfer, potential damage to equipment or the environment, and in countermeasures for limiting consequences in the case of accident. So that is why, if you look at the test launch of the Starship a few days back, okay, this is the 11th test flight of the Starship. Of course, every test they have something to learn, something to understand, something to take lesson, and new technology being improved. Okay, so one of their countermeasures to avoid accidents is to terminate, to abort, to terminate, and etc. And sometimes, of course, they have to pay a lot of high price costs if accident happen. But the thing is, they learn a lot of lessons, and they came out with find a lot of solution, mitigation, experience solution, as well as new technology breakthrough. Okay, so it is kind of good example in our era now to see how the development of Starship, the test of Starship, if you can still remember, how does the Falcon 9, the reusable booster, this technology came 2 or 3 years back. It is actually quite a marvel technology, something that we think that it is a dream to be true, but it happens already, where you can reuse the booster and can reduce the cost of launching. Like I say in my first class, before this, to launch a 1 kilogram of payload into the space, it costs tens of thousands, $40,000 per kilogram. But because of this new technology, you can reuse the booster, you can refill the propellant, and the booster can safely land it. It can reduce the cost to only few hundreds, and later on maybe few tens of dollars only. Okay, and of course, when you use this high energetic propellants such as fluorine and hydrazine, dumping and or spilling the toxic liquid contaminates subterranean aquifers and surface water. This and their vapors pollute the air. You can see that the launches of rockets, one rocket launch every 3 days in the world, is not that many as compared to commercial aircraft where you have tens thousand per minute of aircraft flying into the air. But actually, rockets where you burn fuel at high temperature produce a ton of carbon dioxide, sulfuric acid, nitrogen oxide, which polluted the air as well at very high range of altitudes. Okay, so you can see later when many companies, startups start to build small rockets, eventually later on it can have you will see you're going to have every day one rocket is launched. Okay, so you can imagine that. So that is why I know that you cannot eliminate pollution, but you can reduce the rate of pollution. Why I am saying that you cannot eliminate pollution? Because when refer back to your thermodynamics law. Okay, entropy should increase. Entropy you cannot eliminate. Entropy should increase. So this is the direction of the nature. But you can reduce the rate of pollution. You cannot eliminate. So that is why more novel fuel is being designed at the moment to build a green propellant type of fuel. All right. So last point is one way to enhance safety against accident, explosion, fire spill is to use gel propellant. So these are some of new technology come into the picture, and as well as hybrid rocket technology is going moving forward, next generation of fuel. Why I am saying hybrid rocket fuel is a next type of novel type of fuel? Because the fuel can be the fuel which is in solid. We can use various type of green propellant fuel. Okay, uh, even though the performance of this hybrid rocket in terms of specific impulse not that high as liquid propellant, but it is fair enough to launch a payload to space. Okay, so this is some of the emerging technology, although it is not that well matured yet, but this is the direction to save the world. All right, I think that is all for this chapter. Like I said, this chapter only the calculation only involve sizing the tank, but you cannot forget the chapter from the theory from nozzle theory, and as well as thermodynamic relation in class, in our second week of class. So that is all for today's lecture. I think I have to finish this class early because we have finished. Any question from the students that you would like to ask? Any questions? All of you understand, eh? Oh, that's good. That's good. I hope you do have the textbook, probably soft copy or hard copy, and you can read through. Usually for your quiz, your midterm, and your final exam, I will take it from the book. I am using three books for my lecture. One is Sutton. The second one is Trevor, and the third one is Marvelous lah. Okay, so like I said, for me, I'm not sure whether Dr. Hugh allowed this. For me, I allow my student to have an open book exam, open calculator, open what do you call it, Excel sheet, and etc. in the exam. I'm not sure whether Dr. Hugh allow you or not, but because I don't want you to memorize the equation, I want you to understand the equation, how to use the equation, when to use the equation. Okay? All right. So, do you have any questions in mind? Are you ready to build a rocket? How was the quiz? Can you do the quiz? Not sure. If you want to ask or do, what do you call it, email me or text me. If you want to ask to do the consultation, you can always email and consult with me. I can give you my email if you need some consultation or questions that you don't understand. So this is my email. You can email me. Okay, you can email me to ask any questions that you don't understand, or if you want to WhatsApp me, this is my number. This one is my. Okay, do you have any question? No, you're okay. Okay.
Yeah, it's all right now.
All right, okay. Thank you, class. Thank you for attending this class. We don't have class next week. Next week will be your midterm break. I will prepare your midterm tests for 1 hour, and I will send this to Dr. Hugh. Okay?
Okay. About quiz,
Okay.
we will discuss with the teacher. So we can give discuss with you so we can know if we can take a book or a book or calculator.
Come again. Come again. I cannot hear you.
Hello, you hear me?
Hello.
About the quiz, our class will discuss with the Dr. Hiếu to see if we can about the exam and the quiz.
Oh, you want to discuss the quiz now with me, or you want to discuss with Dr. Hugh?
Yes, our class will discuss with Dr. Hill.
Come again. Can you repeat? Can you repeat, brother? You want to discuss the quiz with me, or you want to discuss the quiz with Dr. Hugh?
Our class will discuss the quiz with Dr. Hill first.
Okay.
Yes. Then we will discuss with you later.
All right, sure. Sure. I hope you have done quiz 0 and quiz 1. I will post another quiz number 2 later, and as well I will draft the test, the midterm test for you. Okay?
Okay. Thank you.
Okay. Okay, thank you so much. Bye. Have a nice day.
Goodbye. Goodbye.
Bye.